All right, hello. So in our Chapter 8 problem set, I asked you to compare series and parallel reactions in an isothermal CSTR. So now I understand that most of you have never taken reaction kinetics before, okay? But one thing I hope you take away from this course is even if you've never taken a course in reaction kinetics, right, I can write down the governing equations for an isothermal CSTR, right? I could say look them up in a textbook. And it essentially just reduces to a system of a couple of equations, right? System of, in this case, couple nonlinear equations, which I could solve simultaneously using fsolve, right? And so even though I don't know anything about CSTRs, I can set up a mathematical model or computer model to describe that system, and then I could essentially perform virtual experiments. I could turn knobs. I could compare behavior for series versus parallel. I can just observe what behavior is like altogether in a CSTR. Right? And so one thing I hope you take away from this class is, even though you don't know anything about reaction kinetics, you could be a pretty good reaction engineer and gain great insight in terms of what's happening in these systems just by setting up the model and using your MATLAB skills to play around and observe, perform virtual experiments and see what's going on. And so what I want to do in this screencast is, again, most of you have never taken kinetics before, and so I just want to work out by hand what are mole balance design equations reduced to. What is my system of equations that I'm trying to solve? Okay, and so the problem statement is pretty detailed. There's more information about CSTRs in the chapter, but I just want to give you some additional information or present it in another way by hand, just to try and help you out in terms of getting things set up. Okay. So now the general idea would be for the case of a single reaction. Okay, so if I have a single reaction happening in my isothermal CSTR, my mole balance design equation, as we work out earlier in the chapter, would reduce to Ni dot minus Ni dot naught. So this is the molar flow rate of species I out of my reactor. This is the molar flow rate of species I into my reactor. So that'll be equal to V times the rate. Okay, so this is the volume normalized rate of generation or consumption of species I. Okay, so this is my rate expression. Okay, rate expression for species I. Okay, it's normalized with respect to volume. So typically when I have a condensed phase reaction, so a reaction that's taking place in liquid phase, I normalize with respect to volume, right? Essentially, I'm making it intensive, right? It's a homogeneous reaction. Sometimes in the future, you might encounter heterogeneous reactions or heterogeneous systems where, say, the reaction's taking place on the surface of a catalyst, at which point you might normalize with respect to the surface area of my catalyst. Okay, but here we're using volume. Okay, and then another way to write my species-specific rate is as the stoichiometric coefficient of species I in that reaction times the overall or general rate expression. Cool. So now it changes when I have multiple reactions. So when I have multiple reactions, okay, what's going to happen is the left-hand side is still going to be the same. Okay, this is just moles coming out, moles going in. So I'll still have Ni dot minus Ni dot naught. Okay, but now, okay, for the species-specific rate, I'm going to sum over all reactions J occurring in my system. So it'll be sum over J, and then it'll be Ri J. Okay, sum over all reactions J, then it'll be the species-specific rate in each reaction J. Okay, so if I had two reactions going on like we have here, right, this would be R1 in reaction 1, or Ri in reaction 1 plus Ri in reaction 2. Okay, and again, we'll write this out in a second. Or not in a second, but we'll write it out. Okay, cool. Okay, or I could equivalently write this as sum over all reactions J, stoichiometric coefficient of species I in reaction J, times that overall or general rate expression of reaction J. Okay, cool. Now, before we do anything else, I just want to play with how we'll often simplify these animals. Okay, so if I leave this expression as is for now, okay, what I want to look at next is, Ni dot. Okay, this would be the molar flow rate of species I, say moles per second. Okay, great. Okay, now if I'm thinking about what I typically have knowledge of, say, going in and out of my reaction, I could calculate a molar flow rate, but it's not something I'm going to directly measure, right? What I'll directly measure would be something more like a volumetric flow rate, right? And we saw how you might, even say calculate that in the last chapter via measuring a pressure drop, right? So what would be more common typically to measure would be, say, volumetric flow rate. And then in terms of, other things that would be more common to measure would be, say, the concentration of my species entering and exiting my reactor, right? And they're all related, so they're all interchangeable. And so here we'll just kind of show how they're all interchangeable. Okay, so this would be my molar flow rate. Okay, so typically when I say concentration, I would think of the concentration of species I is going to be Ni, moles of species I, divided by that total volume. Okay, well, when I have flowing systems or open, or systems such as this, when I'm dealing with molar flow rates, right, what I would typically do is I could recast that as the molar flow rate divided by the volumetric flow rate. Okay, so Ni dot over V dot. Okay, so this is the, say, molar flow rate of my inlet stream, volumetric flow rate of my inlet stream. Okay, that's equivalent then to the concentration of species I in my inlet stream. Okay, cool. Okay, so Ci I can write as Ni dot over V dot. Okay, now Ci, say, not that, so remember this is exiting, that's entering my system. So Ci not versus Ci, this is concentration exiting my system. Ci naught would be what's entering, okay? And that would be, say, an Ni dot naught over V dot naught, okay? But if we assume that, say, my reactant is dilute, okay, so my reactants, the actual molecules or components that are reacting and being generated in my system are rather small, okay, we can say that our volumetric flow rate can be assumed constant. So I could write that as, say, an Ni naught over V dot. Right, the same V dot is there. Okay, so concentration is great. Okay, but here I have V and not volumetric flow rate. Okay, so how am I going to get volumetric flow rate into here? So essentially, I would need this to instead be V dot. Well, what we're going to do is how is V dot related to V? Well, okay, this is units of, say, centimeters cubed per second, volume per second. V has units of, say, centimeters cubed. Okay, so what we end up doing is we divide by what's called the space-time. Okay, and so how you could picture the space-time is it's essentially the average time a fluid element would remain in my reactor, right? And so if I were to solve for tau would be equal to V over V dot. Okay, so now this is the volume of my reactor. This is the volumetric flow rate of fluid entering and exiting my reactor. So V over V dot is going to have units of time. Okay, and this will correspond to essentially the average time a fluid element remains in my reactor. Okay, tau, right? So tau has some physical significance. Okay. So if I were to plug this all into our rate expression, right? So first let me plug in V is going to be tau times V dot up here. Okay, then I'll divide through by V dot. Okay, what I'll have is, so Ni naught minus Ni dot naught is equal to, so for V, okay, if V I'm going to replace with V dot times tau times sum over J nu Ij Rj. Okay, so now if I divide through by V, okay, and I'm assuming that the volumetric flow rate in and out is the same, okay, so divide through by V dot, okay, Ni over V dot is Ci, Ni, that's a naught up there, over V dot is equal to Ci naught, and I get that Ci, the concentration leaving my reactor, minus that going in, is equal to tau times sum over J new ij, okay, that's meant to be a comma, rj. Okay, cool. All right, so I'm going to add another page in case we continue on. Now, before we talk about how we're going to what our mole balance system of mole balance design equations reduces to for this problem, we're going to talk about stoichiometry a little bit. Okay, and so if I were to look at the series reaction case, okay, so in our series reaction case, okay, A is reacting to form B, where B is my desired product. Okay, and we're calling that reaction 1. Okay, then we have an undesired reaction happening where B is reacting to form some species C. Okay, so C is going to be our undesired product, right? We want to make B, okay, but what happens is B is consumed in the secondary reaction to form C, which is an undesired product. Okay, so if I were just to think about the stoichiometric coefficients of each species, okay, well, okay, let's look at just A. Okay, what am I going to have? Well, the stoichiometric coefficient of species A in reaction 1, okay, will be -1. Okay, if it's a reactant, it's going to be negative, right? Times, right? Essentially the coefficient of my balanced reactant or reaction. If it's a product, it's going to be positive, so +1 times the coefficient in my balanced reaction. Stoichiometric coefficient of A in reaction 2 is 0. It's not present. Okay. For B, I would have that the stoichiometric coefficient of B in reaction 1 is a +1. Stoichiometric coefficient of B in reaction 2 will be a -1. It's being consumed. Okay. Now for C, stoichiometric coefficient of C in reaction 1 is +1. Okay, it's a product. Oh, sorry. In reaction 1, it's 0. Stoichiometric coefficient of C in reaction 2 is +1. Right? It's my product. It's being generated. Okay. Cool. Now, the other thing I'll go quickly and flashback is we have all these, simple first order reactions we're looking at. Okay. So, here's all my R1s and R2s. Essentially, we're just going to have rate constant times the lone reactant in each case. Okay, so here's my stoichiometric coefficients for reaction 1 and reaction 2. Okay, now in terms of my general rate expressions for reaction 1, okay, it's just going to be K1 times concentration of 2, okay, and R2 is K2 times the concentration of B. Okay, and so another reason or another benefit of putting concentration into my mole balance reaction is when I plug in R1 and R2, it's also going to have, use concentration of my reactant in this case. Okay, and then for K1 and K2, okay, so I won't completely write it down. Well, I can, right? But K1 is called my rate constant, and so it's going to be given by this Arrhenius equation. So it's going to be a K0.1 is how it would typically be written, times the exponential of the negative activation energy of reaction 1 divided by RT. Okay. Now in the problem statement, you're given activation energy. This is my molar gas constant. T would just be my temperature. So we have all of these. Okay, and you're going to be given the value of K0.1, and then what you're going to be told to do is, so K2 is going to be some K0.2 times exponential of negative E2 over RT, right? And so again, you're going to be given all of this, right? And in fact, this is going to be the same as reaction 1. And what I'm going to ask you to do is play around with cases where, say, K0.2 is equal to K0.1, K0.2 is 0.1 times K0.1, or K0.2 is 10 times K0.1. So you're just going to play around with the relative value of those. These terms will be the same, right? And so like K1 I would plug in here, K0 or K2 I would plug in here, where you're going to be given all of this information, right? And so you see this is very quickly going to become a linear equation where I'd plug these into my mole balance design equation. All right, and so if we just keep playing with the series case, we have stoichiometric coefficients, we have rate expressions, right? What are these mole balance design equations going to look like? Well, okay, for A, okay, we're going to have a mole balance design equation for A, B, and C, right? I have Ca minus Ca naught is going to be tau times, okay, nu A in reaction 1 times R1 plus nu A 2 times R2. C, this is B, CB minus CB naught is tau times nu B1 times R1 plus nu B2 times R2. And CC minus CC naught is going to be tau times nu C1 R1 plus nu C2 times R2. Okay, cool. Okay, and so essentially what we're going to have, right, is we're going to have the system of three coupled equations. Okay, they're going to be coupled in the sense that R1 and R2, so R1, okay, is going to be a function of Ca, R2 is going to be a function of Cb, right? So when I plug in R1 and R2, R1's a function of Ca, R2 is a function of Cb, right? So I would plug that into each of those expressions. So I end up with a system of three coupled nonlinear equations that I would need to solve simultaneously. What do I solve them simultaneously for, right? And so the setup is, I ask you to look for, essentially to look at the concentration of A, B, and C as a function of space-time. So what that's going to scream is for loop, right? So I'm going to set up a for loop where I loop over a range of tau values. Okay, and for each tau value, so each iteration, once I specify tau for that iteration, tau will be set, and I'll solve my system of three coupled equations for Ca, Cb, and Cc. Okay, so I set up a for loop where I loop over a range of taus. Each loop iteration for given tau, I can solve for Ca, Cb, and Cc. Okay, so I'll collect those in, say, vectors or, use a matrix, where at the end I have Ca, Cb, and Cc as a function of tau. Okay, and then, at the end I can go and calculate fractional conversion and selectivity, like the problem statement asks for you, right? And so fractional conversion is just, if A is my, main reactant, right? If A goes to B, and then it's just B is my reactant, my second reaction that's being, consumed. So if I was just looking at how much of A, my reactant, going into my CSTR is consumed, right? Well, it would be, let's see, how much went in relative to what's coming out, okay, divided by how much went in the first place, okay? Fractional conversion, okay? Selectivity we're also asked for. Okay. Oh, and so this should go to 0 when all of my A is, let's see. So it'll go to 1. So initially it'll start out at 0, right? You can almost think of it as like the percent of A that's being consumed in my reaction. And so what'll happen is in the long time limit or long tau limit, the longer I allow that fluid element to stay in my reactor, the smaller and smaller A is going to be, right? Tau is the effective time that I allow my fluid element to remain in the reaction, or the average time a fluid element remains in the reactor. So the larger the tau value, the smaller or less A I expect to be coming out my reactant. So in the large time limit, Ca is going to essentially go to 0, and Fa will go to 1. Okay. Now selectivity, okay, if B is my desired product, okay, and C is my undesired product, okay, when I talk about selectivity, it's just how much of my desired product's coming out relative to my undesired product, right? And so that would just be Cb over Cc. Now, the thing that you just have to be careful with is when you plot this is, say, in the limit that time goes to 0, right, I only have A present, right? A's going in. So I don't have any B, and I certainly don't have any C, right? And so this is going to be, 0 over 0, right? So that'll give me NaN. But then even if I look at time slightly greater than 0, what's going to happen is B's being generated in reaction 1, right? A goes to B. So really small times, I'll get a little bit of B. but I'm essentially going to have virtually no C, because the second reaction is dependent on the concentration of B. Concentration of B is really small, and so that rate is really, really slow. So, initially what's going to happen is so say both of those Ks were the same at time equals 0, then reaction 1 is going to dominate, right? Then as A is consumed and B is generated, right, then reaction 2 is going to begin to, increase while reaction 1 slows down. So what I'm trying to say is, when you go to plot this, is what you may find is that small times you get huge values, right? Because at low times, right, this term's going to go to, essentially infinity, right? You're going to have, a number over 0. It's going to go to infinity. And so just take care when you plot it. If you get some huge value that then, comes down, that's normal. Okay, but cool. So you're going to get a for loop, where you're going to loop over tau values. For each tau, you're going to use fsolve to solve my system of 3 equations for C, A, C, B, and CC. Right? Now, if this is, my error function, right, then I'm going to need an anonymous function to at least pass, tau, and then you should probably also pass those other parameters each iteration to my error function, which then will solve for that unique case each iteration. Okay, that was series. Okay, if I'm talking about parallel, it's just reaction 2 is going to change, right? It's going to be A goes to C. Okay, so stoichiometric coefficient of A, B, and C. Let's see, stoichiometric coefficient of A and B will change, and then my rate expression changes, and the R2 is just K2CA. But then, for the most part, everything else is the same. Mole balance design equations is the same in the general cases. I have it listed here. Selectivity is the same. It's just, some small slight updates. Okay. All right. So in the interest of completeness, all right, so what's going to be different is when I have parallel. Okay. Now I'll have A goes to B in reaction 1. Okay. Where B again is my desired reactant or desired product. But I'm going to have a side reaction where A also produces C. Right. B is my desired product. C is undesirable. Okay, so if I look at stoichiometric coefficients now, nu A in reaction 1 is going to be -1. Nu A in reaction 2 will also be -1. For B, I'm going to have nu B in reaction 1 will be +1. Nu B in reaction 2 will be 0. For C, nu C in reaction 1 will be 0. Nu C in reaction 2 will be a +1, right? It's my product. Okay. Now my rate expressions are still the same, right? So R1, well, almost the same. It's going to be a K1 times CA. Okay. R2, right? A is still my reactant, and so I said let's take this to be K2 CA. But your expressions for K01 and K02 would be the same. And so what I would probably do is, whether you solve parallel or series first, I think in the problem I listed as parallel being first. But I would solve one case first, because then all that'll change for the other is if I keep my bowl balance design equations in that general form, will be the set of stoichiometric coefficients. Right? So solve one. If you can solve series or parallel, then you can readily solve the other case. Okay, so there's my tips for you. Hopefully with that you can get it set up and solved without a problem.